you get the browser disappears on me, but that's fine, I guess.
Okay.
Okay, so this is going to be just kind of a very somewhat briefish overview of like what is a synchrotron and what is a beamline, and a very remedial explanation of how we get X-rays and what we do with those here at the facility. And fundamentally, why would you want to use a synchrotron at all to do anything? So the X-rays that are generated, and this talk is going to be very specific for the advanced photon source, because I did a version of this with stuff there, but it doesn't matter. It's appropriate for any synchrotron anywhere. The X-rays are generated by when you can force a change in direction of some high energy particle beam. And at the APS, this is electron. And in fact, most synchrotrons, this is an electron beam that they use in the storage ring. Some synchrotrons have used positrons, but I think most synchrotrons now use electrons. And the potential, for example, at the APS is 7 giga electron volts with a 100 milliamp current power in the storage ring. There's two fundamental ways that you can then force a change in this electron beam. You can use, the first one to be an undulator or a wiggler. These things will give you a higher flux beam, but a lower bandwidth beam. The other thing you can use is a bending magnet, and this will give you a lower flux X-ray beam, but a higher bandwidth. And so what I mean by bandwidth is the energy of the X-rays that are produced by the device. So, for example, if you turn on the light on the flashlight on your cell phone, you get white light, which is a very high bandwidth light, because you're essentially getting all the colors of the rainbow that are combining together and giving you white light. And so, if you had just green light, then that would be a much reduced bandwidth or lower bandwidth light that you would see. And just an example of a sector for this. So if this is all of these colored boxes on this are representations of magnets in the storage ring, and all of everything that happens is determined by with electromagnets, and that, or in some cases now permanent magnets, because they can make permanent magnets much better. The electromagnets are used to effectively steer the beam, and also, well, as part of steering the beam, you're changing the direction of the beam, and that will give you the X-ray production that I mentioned in the previous slide. And so in this top portion, it would be if you were looking down from the sky at the top of the storage ring. There's a number of these blue and yellow magnets. They're quadrupole and sextupole magnets that are used for steering. And then there's this very large red dipole magnet, which is one of the bending magnets that I mentioned. And then, so this will cause the X-rays to then, they come in a straight line, and then they'll bend ever so slightly, and then they'll move in another straight line. So even though we call it a storage ring, it's really not a ring. It's a series of straight sections between these yellow magnets that are marked as SD, and the blue quadrupole magnets. And then you get a section where it's bent with a dipole magnet, and then you get another straight section, and then another bent section. So it's basically a series of straight sections with bends in them, and that's how they, you know, end up circulating things through the storage ring. So an undulator is basically a series of magnets, and so the electron beam will come through the magnet from the back right of this slide, coming into the front, and as it comes through this array of magnets, the beam will start to move or you know, undulate side to side. Okay, and so these magnets are then, you know, you get opposite magnets in this large array, and you get the beam moving side to side or wiggling. Hence the name for one of these things, other name of a wiggler. So the beam will move side to side very rapidly through this array, and every time that it makes one of these directional changes, you get X-rays produced all in a straight line along the through the center of the undulator. And so this gives you an extremely intense, very collimated X-ray beam coming out of the undulator. So the undulators are for this reason very, this is what most people want to use for most experiments now, because you can get an extremely intense X-ray beam that you just really can't get out of a bending magnet beam line. And so this is just a kind of a picture to give you an idea of scale of one of these undulators, and you can see there's the magnet array between these two large jaws. These are all mechanical, so that they can move these closer together or further apart, and the distance that these are from each other will determine the energy of the X-rays that you get, so if you want to change the energy for the X-ray, then part of what has to happen is that the distance between the jaws on this undulator has to then be changed. And here's an example of one of these inside the storage ring, which you can see. Whoops. Can you see my cursor when I move it around?
Yes. Yep.
Okay, so you can see right here, there's the magnet arrays for one of these undulators, and this is actually, I believe, two undulators that are stacked, one in front of the other, and so this would be what they call the tandem. I'm blanking right now, but so this is the kind of arrangement that the AMX and FMX beam lines would have. So you've got an upstream undulator here that would be, for example, supplying X-rays to AMX, and then a downstream undulator here that's then supplying X-rays to FMX. And this is a way that, you know, some engineers a while ago figured out a way that they can basically put two undulators, slightly smaller undulators, in the space of one straight section, and then you can get two ID beam lines out in a place where you normally only would have gotten one ID beam line out. So after you get X-rays out of your synchrotron, then you've got to clearly do something with these. And for the typical beam line, you'll want to be able to select the energy more specifically that you want. So you'll have a device called a monochromator. You'll want to be able to then focus these X-rays, because the size of the beam may be significantly larger than then what it is that you want to be using. So typically we'll use mirrors to provide focusing for this. So this comment here that X-rays can only be focused reflectively is a slightly out of date. You can also use these kind of very specially machined blocks of metal that will focus optics convexly, kind of the way light can be focused with like a regular glass lens. There'll be a series of slits and masks that will alter the beam size, and then you'll have a shutter that will control the X-rays onto your sample, a goniometer or some kind of sample mount, sample stage, depending on what it is that you're trying to do, and then a detector to record the results of the diffraction experiment or whatever it is that you're trying to do. It could be if you're doing X-ray fluorescence, then you're going to have a fluorescence detector, and you're not going to really be measuring diffraction data, but you're still measuring X-ray energies. And so at the beamline, they'll typically have in what we call a first optics enclosure. So in this picture from the right-hand side, this portion over here is the wall where where you would go into the storage ring on the other side of the wall. And then on this side where the picture is being taken, you start getting the experiment equipment that's sitting out on the floor that you would see. And this is the first part of the things that the X-rays are exposed to the beam line. So that will transit down this large vacuum pipe. This portion right here that has all these pipes and tubes on it are a series of slits that will slit down and reduce the size of the beam that's coming out of the storage ring before it goes into the monochromator, which selects the energy, which is this large circular tank here on the left-hand side of the picture. So one of the more typical ways that people will arrange their monochromator is something called a double crystal monochromator. And it's called that because there are two crystals in the silicon crystals, typically, in the monochromator. And the first crystal will provide energy resolution. So as I had mentioned in a previous slide, you get some bandwidth of X-rays coming out of the storage ring. And for most experiments that you're going to want to do, you're going to want to have a much narrower bandwidth of energy, or basically as close to a single energy of X-rays as you can get mechanically. So the first crystal in this monochromator will provide energy resolution, and the second crystal will provide some amount of limited steering, but will reflect the beam back down the beam line. And typically these crystals, for most applications, are silicon. They could be diamond or even something else. Silicon crystals will require cooling with liquid nitrogen. Diamond crystals don't require any cooling and can take the X-ray power that's delivered to them. The second crystal can also provide focusing, which is called sagittal focusing and sagittal bending on that crystal. This is actually how we do focusing at NYX, instead of having a separate mirror that I'll show you in a little bit. So this is a kind of a little bit better picture, or a different picture of the monochromator that's in this tank. This device here on the right-hand side is a liquid nitrogen pump. And so this is pumping liquid nitrogen into the monochromator that then will provide cooling in a loop. So it goes in one side and basically then comes back and gets returned to this tank. So it just circulates liquid nitrogen through this device to keep it cool. And to kind of give you an idea, you can get hundreds to thousands of watts of power getting delivered onto a 5 millimeter square spot on your crystal. So there's a very tremendous amount of energy that's being delivered into this equipment, and loss of cooling power can mean damage to the equipment. And you can occasionally hear about people having things misaligned and then vaporizing metal in the X-ray beam because they had a misalignment in their equipment. So the inside of one of these looks something like this, and so the X-rays are coming in from the right-hand side through this port, and they're then going to exit the left-hand side through this port here. The picture on the left-hand side doesn't have the crystals in it, but the picture on the right-hand side does. And so you're looking downstream through this, kind of in the direction that the X-rays are going to come in. And so you can see this copper-colored shield here, and then there's this little slot that's cut out on it. And so the X-rays will go into this slot, hit the first crystal that's underneath this shield, and then the X-rays will then come up and then hit this crystal. So this square-shaped thing is the second crystal, and then they'll bounce down. So what you're getting is the X-rays will come in, refract up, hit the second crystal, and then go down. And so the second crystal really just exists to steer the X-ray beam back down the beam line. And so you'll get a little bit of an offset from the incoming X-rays will be at some level, and then the outgoing X-rays will be slightly higher or lower, depending on the orientation of the two crystals. Whoops. So after you get your X-rays through the monochromator, you'll need to focus them in some fashion. And the X-rays are typically, in most cases, reflected off of curved mirrors. And the mirrors can be then coated in some fashion to alter their reflectivity. And this is typically with some metal like platinum or rhodium. If you've got a fairly low energy X-ray beam that you're interested in, then you could probably get away with having no coating and just using glass. And these mirrors will typically be bent in, or you'll get the bend in primarily two different ways. You'll have what they call a two-moment bender, where the mirror is just physically bent using two motors that'll apply pressure on the two ends of the mirror and then bend it. And the other method is what they call bimorph mirrors, where you take the mirror that has piezoelectric elements embedded into it, and then as you apply force to the piezoelectric elements, then that will apply a bend into the mirror that you've got. And so these are just two examples, well, two pictures of the same mirror. So this mirror is about 1 meter long, and you can see that there's 3 different coatings on it. There's a middle stripe that has basically no coating, and then there's 2 coatings on the edges. And you can see there's this brown stripe on here is oxidation from the X-ray beam that's been striking it. And so this is a 2-moment mirror. And what would happen on this is you have motors or some gearing and mechanics attached to both ends of this mirror that would pull the mirror apart, or they would pull against each other, which would effectively then put a curve into the mirror. And it can be a very gentle curve. I mean, they talk about, let me see, curvatures of radius in like between probably 6 and 14 kilometers. So you're not putting a huge bend in this thing. You're just putting a very gentle, very small bend in it. But I kind of think the fact that you could bend a fairly large piece of glass like this at all, rather amazing. And so this is just an example of a 2-moment bender in a vacuum chamber. So the wall on the one side is taken off, and you've got a motor here on one end of the mirror, and another motor here on the other end of the mirror. And depending on how you change the forces on this, then you'll change how this mirror is bent. And then you've got these little springs in the middle to help keep it from sagging too much, because you can definitely see gravitational effects from this that'll affect how the mirror bends. And so this is just an example of some bimorph mirrors. And you're looking on the edge of one set of mirrors right here, and you can just see all these wires are then connected to the piezo elements that are these little kind of standoff things that are poking up off the top of the mirror right here. And so this mirror is then set up in what they call a KB pattern or KB style arrangement, which is better shown on the right-hand side. So you've got one mirror that's flat face up, and you've got another mirror that's standing up on its edge. And so the mirror that's face up, when it's bent, that will focus things vertically. So that'll squash things down vertically. And then the X-ray beam will come off of that, hit the mirror that's standing up on its edge, and then that will squash things horizontally. And so you'll get focusing in the two different planes using the two sets of mirrors that you have. And so this is I mentioned this is a KB pair, and that's the KB stands for Kirkpatrick Bayes, which I presume are the last names of the two people that figured out how to do focusing in this sort of arrangement. But this is a fairly typical way to be doing X-ray focusing at any beam line. So really, why would you want to use a synchrotron at all? Well, the fundamental reason is that you get significantly more intense X-rays, which gives you much faster data collection, which then can lead to more data sets that you can collect in the amount of time that you have. And giving more intense X-rays also lets you interrogate much smaller crystals than you would be able to do, say, on a home X-ray generator that you have. You can do high throughput data collection at a synchrotron. You can change energy at a synchrotron. Now, some home generators will let you choose between maybe two different energies because they'll have two different anodes that they can swap back and forth. But at a synchrotron, there are many beam lines that gives you the opportunity to change over a very wide range of energies. And so this can give you the opportunity to do anomalous scattering experiments, which was really the primary way that people have been doing structure solution for a very long time. And it can also help you validate presence of metals or other elements in your structure, which you can do by changing the energy and doing X-ray fluorescence techniques. And so, really, one of the primary reasons is just X-ray flux. So if you looked at a couple of different home generators, you could get in the neighborhood of like 10 to the 8th or 10 to the 11th photons per square millimeter. Stanford will get you in the low to mid 10 to the 11ths. And APS ID beamline can get you in the 10 to the 13ths photons per second. I think they can get 10 to the 14th photons per second here at NSLS2. So this is really the huge benefit to using the synchrotron, is just a significantly higher photon flux. Now, the downside to this, particularly for biology, is radiation damage. So, for example, here's a frame from a Thawenton crystal with no attenuation, and it looks fantastic. This is a textbook example of good protein diffraction. Now, if you collect data with this, then clearly you can end up with radiation damage. So I've got on the left-hand side, this is the first frame. And on the right-hand side, this is frame 180. And you can, I think, fairly clearly see that, in the first frame, we had diffraction all the way out to the edge of the detector. And now we're getting, diffraction kind of a little bit just slightly past the water ring. The spots went from being very nice and pinpoint on one side to they were starting to get a little bit smeary on the other side. So this is kind of one of the downsides to having a huge amount of flux, is that you can just as easily destroy the sample that you've got, which if this is the only sample that you've got, you need to make sure that you don't destroy it before you get your data collected, so that you can solve your structure or do whatever it is that you want to do with this. So I'll just kind of briefly go over some mistakes that I think that people make when they go to the synchrotron. And primarily it's not knowing what it is that they want to do. I think people want to do things and they understand it at a higher level, but maybe not at a lower level. Like how much data do they need to be collecting? Are they trying to do an anomalous scattering experiment? Are they, what is it that they really need to be getting out of their data, and hence their synchrotron trip? And kind of not knowing these things at a fundamental level can, I think, make for a difficult experience. I think like wasting time on irrelevant tasks at the beamline, or trying to adjust beamline equipment. I've certainly caught people doing this. Not immediately analyzing their data. Now, a lot of beamlines nowadays have automated data processing, so you can get fairly quickly some idea about what's going on with your data. If that's not the case, then if there's a group of people going, then you should have some people collecting data and some people working on the analysis on that. So the sending unsupervised students portion was, I certainly know that you're all teachers, and this is more geared at frequently we would get graduate students that are very junior coming to the beamline or trying to do experiments at the beamline, but not really knowing what it is that they're supposed to be doing. And I think a little bit of an expectation that the PIs would kind of foist their students off on the Beamline staff and expect us to be doing their taking over the training aspect of this. And this just becomes very, very difficult as far as getting, going back to the not knowing what they want to do. I've had students show up at the Beamline saying, I want to do an anomalous experiment, but I don't know what metal to do it on. And that's just kind of problematic. Really not asking questions of the staff when you're here. I mean, the staff should be experts at using the Beamline and getting the most out of the Beamline. And so if you have questions or concerns, or you don't understand something, then you should certainly ask the staff. Maybe there's some newer, better way to do something, or a feature in the software that you don't understand, or a better way to do analysis. But definitely don't be shy about asking the staff how to do things at the Beamline there. And I think the last thing is just not reporting problems. A lot of my job as the Beamline scientist is to provide the facility to the users, to you, the users, so that you can do the experiments. And I mean, I can do some amount of validation to ensure that things are working, but there are times when maybe I'm not aware that things are not working correctly, or that something has happened or changed. And so if the users then need to tell the staff that things don't look like they're working correctly, or I'm not getting the results that I expect, and then we can help get that sorted out for you. So just as a quick summary to this, I think using the synchrotron really can make a major contribution to anybody's research program. I mean, you can do experiments here that you just cannot do at home on a home source, and so it's definitely a facility that people need to be aware of and not be shy about wanting to use. And for a successful trip, and this is more geared towards protein crystallographies, you need to use automation-friendly crystallization mounts. You need to have an idea of what it is that you need from each of your projects, know how you're going to collect your projects, establish some sort of a data naming convention, or understand how your data is being named and stored, because this is then leads into the data management scheme that people will get multiple trips out to the synchrotron every year, and you can very quickly end up in a situation where you either don't know where this data came from. You collected it from the Beamline, but you don't know which trip you collected it from. You don't know which crystallization condition the data was originally associated with. And so you need to have some sort of a data management scheme in place so that you can track where your structure came from as far as the data and the crystallization conditions. And so that's all I think I've really got for you right now. I'm happy to answer any questions.
I have a question about those undulator magnets. So those are mechanical, so those can be adjusted up and down.
Yes. Yeah.
Does that happen? Can that happen in real time? Like as you're running data collection, you realize, ooh, our spot's not where it should be, or we need to focus the energy more, or is that something that happens before people come to the Beamline and they start collecting?
Yeah, so that would happen before you go to the beam line. So that's really part of the when you change energy, then you'll change the undulator magnets will the distance between those two will change. So once that's set at some energy, then they shouldn't change. So basically, what would happen if you change the undulator magnet distance and you didn't change the monochromator energy, is your intensity will just drop off the cliff. So that's one thing that you would notice, is that your beam intensity would be significantly lower than expected. But that's probably something that you wouldn't notice, but the beamline staff would notice during setup.
Okay. So there's a lot of physics involved in this. So for the students that are here with us that are interested in the physics aspect of things, there's a lot of talk about mirrors and using crystals to deflect the electron beam and try to narrow the electron beam, the X-rays, and try to narrow the X-rays down and focus them. So that's a huge piece that we don't get to see very often. When we go to the beam line, we just see all these pipes and tubes and big silver boxes and don't really know what's going on inside of them. So now we understand that, how these pieces come together to work to allow the beam to be focused and precise, so that it strikes the crystal exactly the way we want it, with the intensity that we need, because again, we want that high energy, we want that high flux, because that's going to allow us to have better resolution, right? Is that correct?
Yeah.
Okay.
Yeah.
All right.
Yep, go ahead. Yeah. It's really fundamentally a gigantic physics and engineering endeavor.
Yeah.
And I want to. I heard this, but I'm not entirely correct on it, that the original synchrotrons, that the X-rays were just kind of produced as an offshoot to the high energy physics stuff that they were doing, and they weren't really, that wasn't really the goal for it. And then somebody went, oh wait, maybe we can use these X-rays for something. And so they then started building these devices specifically to make X-rays.
So I just want to mention to the students that Kevin is a beamline scientist who very often assists us when we are at, especially the NYX beamline, but even just with preparation of our samples, he provides a lot of advice. The data analysis, he's really instrumental to our protein crystallography Spark, and has introduced us to other collaborators as well. That has really helped the Spark program to move forward. So Kevin is invaluable to Spark, and we really appreciate that you were able to come here today. Thank you.
Oh, sure. Sorry, it was a little late.
It's okay. It's summer. We're okay. The other thing that Kevin also is tremendously helpful with, he's actually instrumental in this, is the preparation of our PDB deposits. He makes sure that everything looks the way it's supposed to, and he assists us through the process of getting all the files together and getting everything deposited. And he's also been involved as a reviewer of our in-house reviewer of our papers as we're preparing those for publication. So Kevin does a lot, and we really do appreciate all the work that he does. He's a major part of our group, and we appreciate it. So thank you.
Oh, thank you.
All right. So that's going to pretty much wrap things up for today. I wanted to show a brief run through of the beam lines that we use, but I can probably do that for Friday. I do want to just leave everybody off with understanding that there are 3 major beam lines that we're going to be working with once the school year starts up. And so I'll explain a little bit more about that. We'll do that on Friday. So it's 10:53. We're pretty much set for the day. So on Friday, we're going to not only wrap up the week, but we're also going to talk about our workflow and our game plan, basically. We're going to talk about the proteins that everyone's going to be working on and the expectations moving forward of what we need to do as a collaboration so that we can gain access to the beam lines. And one of the beam lines we'll be using is Kevin's beam line, which is the NYX beam line. And as soon as the schedule is up, we'll start looking at dates on that. We'll be able to share with everybody, and the teachers will all talk about dates that work best and how we can best get our students there, along with Sharon, making sure we can get everybody badged and figure out the timeline for that. That's it. So we're going to wrap it up now. It's just a little before 11. So everybody, thanks for being on, and we will see you on Friday at 10 o'clock. All right. Have a great day, everyone.
Thank you, Kevin.
Thank you, Kevin.
All right.
Thank you, Kevin.
Bye.